Hello, my name is Alan Coley and I'm from the Department of Mathematics at Dalhousie University, and I'm going to give a talk on open problems in mathematical physics. A couple of comments about the format. I've used Red Outliner to remind me basically what I want to say in the talk, and I'm using blue effectively for definitions and for details and exact statements of problems, although here that doesn't quite fit the definition. So the idea is to present a list of open problems in mathematical physics. This talk is taken from this reference here, where everything is given in more detail. In particular, I'm going to refer to several famous lists, and all of the questions in these famous lists are displayed in the paper. And there are some sections in the talk where I go into very little detail, and I may have an asterisk here to indicate that the details are found in the paper. There are going to be 6 sections. The first section is an introduction, which I'll do in this video. The second is a definition of what I mean by mathematical physics and the types of problems that would be included in such a list. Sections 3, 4 and 5 are open problems in general relativity, the quantum realm and cosmology. And if time permits, the last section is actually a list of all of the 42 open problems that I've described. So, to begin with, let me start with the introduction. This is really a little bit of a historical context. I want to sort of describe different areas of mathematics and why we divide it into pure and applied and what it actually means. Try to give you a sense of the cultural role of questions in mathematics. It has a unique role in mathematics that doesn't perhaps occur in other topics, and maybe talk about one or two of the very famous problems that have captured mathematicians' imaginations. So there are essentially two branches of mathematics: pure and applied. Of course, this is an artificial barrier. And the actual mathematics that mathematicians do is exactly the same. It's possibly just the motivation between pure and applied mathematics is slightly different. You might say that pure mathematics is concerned with mathematics for its own sake, proving theorems, and it's assessed to be a good problem. A pure mathematics problem is assessed to be a good problem if it leads to new fields in mathematics. Applied mathematics is also concerned with establishing facts about the real world. So the problems themselves might be motivated from science, and in particular physics. As I said just a moment ago, noted problems in mathematics have always been important and a part of the mathematical culture. In olden times, it was a test of one's acumen and was a recreational endeavour. And indeed, the central figures in mathematics have always played an important role, and so what they think to be the most important problems have always been associated with additional importance. Now, I have 2 examples of problems that have occurred in the past that perhaps give you a sense of this cultural heritage. The first one is problems in solving cubic equations, which is the problem that's outlined here. Let me just go to the second problem just to give you an idea of the type of historical context. So famous mathematician John Bernoulli published a problem, and the problem was this. So this is in the 17th century. Find the curve connecting 2 points. They're at different heights and not on the same vertical line, such that a body acted upon by gravity only will fall the shortest distance. So this is called the brachistochrone problem. Now, I'm not sure whether this is true, but the folklore says that Leibniz and Bernoulli were confident that you could only solve this problem using calculus. And at the time, the only people that were known to understand calculus was Leibniz in his group and Isaac Newton. Although at that time there wasn't a communication between the two groups, and so in a sense Leibniz didn't really know where Newton was. So the idea is, or at least the folklore is that this problem was posed in part to find out what Newton knew. Within 1 day of receiving the challenge, Newton sent in his solution. When Bernoulli announced the winners of the contest, he named Leibniz and L'Hopital as the winners, and an anonymous winner, which he believed was Newton. And he said, or the quote is, Bernoulli recognised the anonymous winner in public with the phrase, "We know the lion by his claw." So perhaps the most famous list of problems is the list of problems published by the German mathematician David Hilbert. All of the problems at the time that he published the problems were unsolved. Several of the problems have been extremely influential in mathematics, in the development of mathematics. Since that time, there have been several people and institutions that have announced new lists of problems, but I think it's fair to say they haven't had quite the same influence as the original questions by Hilbert, although I will mention a couple of these lists in a moment. So Hilbert's 23 problems were published in 1900 and ranged over a number of topics that were contemporary at the time. Some of these problems were stated precisely enough to enable an answer, others were not. In fact, some of them were formulated so imprecisely that I think nowadays one wouldn't even include them as legitimate problems in mathematics. At the time of publication, all of the problems were unsolved. Some of them were very influential. These numbers, H11 and H16, are the numbers of the actual problems in the list. The full list is in that paper reference that I gave, and the unsolved problems I'll actually indicate in a moment. And some of the problems have actually given rise to solutions that have actually garnered a lot of attention. One of the most noteworthy problems is the so-called Riemann hypothesis. This asserts that all non-trivial zeros of the analytic continuation of the Riemann zeta function have a real part of a half. So the Riemann zeta function is a function that appears in an analysis, and this problem concerns the location of the real parts of the zeros. And as it says there, it's still an important problem and would have an important role to play now if it were to be solved. This is indeed a problem in mathematics. I don't think anybody would claim that this is a problem in mathematical physics. However, these lines get blurred because even this famous hypothesis, which is a problem in pure mathematics, has a potential application in physics, in the sense that the energy eigenvalues of certain distributions of random matrices, which are important in nuclear physics, are given by solutions of the Riemann zeta function. And there are in fact experiments that look for these energy eigenvalues, which actually pictorially give you the zeros of the Riemann function. So you can actually see the Riemann eigenfunctions in the experimental setups. So here are the 4 unsolved problems of Hilbert. The first is the mathematical treatment of the axioms of physics. The second is the Riemann hypothesis. And there are 2. So these are the problems that are unsolved today. And H12 and H16 are problems in pure mathematics. Most of the original problems were in pure mathematics. Only a few of them would be regarded as problems in applied mathematics. But H6 is an interesting one. It's basically to put certain areas of physics on a more formal mathematical level. It's very vague, and as we will see with problems I describe in a moment, the problems that probably suit themselves to or could be called problems in pure theoretical physics, mathematical physics, are problems where you can actually describe systems by differential equations, and you can pose a well posed mathematical problem about the behavior of the differential equations. Even though it was vague, Hilbert did try to direct attention towards 1 or 2 particular areas of physics, and namely he looked at the axiomatic treatment of probability in statistical mechanics, and limiting processes to the laws, using limiting process, well-defined mathematical limiting processes when looking at the laws of motion of continuous media. And as it says there, both of these problems to some extent have some, there have been progress, but the original problem was too vague and too vast to perhaps hope to answer it in totality. Sometime later, namely a century later, Vladimir Arnold suggested there should be an update on the questions, and he basically inspired Stephen Smale to produce an updated list. These are called Smale's problems. Of course, 2 of the problems are Hilbert's original problems, in the sense that the unsolved problems of Hilbert, not taking into consideration the mathematical physics axioms, are still unsolved problems, and so it's still regarded as important problems. Another problem was the Poincare conjecture. The Poincare conjecture asserts that in 3 dimensions, a sphere is characterized by the fact that it's the only closed and simply connected surface. I said that incorrectly, but in 3 dimensions, it's the only closed and simply connected surface is a sphere. This was actually solved by the Russian Perlman in 2003 using a relatively new branch of mathematics called Ricci-Flows. And this is an area of mathematics that now is very topical. Here are the list of unsolved problems. P equals MP. I'll talk about that in a second. S4, you can see the designation. S is Smale's list, problem 5, and so on. This problem here, S8, is basically putting financial mathematics on a well-posed, rigorous mathematical basis. Problem in linear program. S10 is problem in pure mathematics. So is 16. 18 is rather more philosophical. And you'll see that S15 do the Navier-Stokes equations of fluid mechanics have a unique smooth solution. So here's the applied mathematics problem, mathematical physics, and one of the realizations of the original mathematical physics problem that Hilbert posed. Just a quick problem. The problem PMP does P equals MP. This has to do with the fact that some problems can be solved by computer by using an algorithm, and the algorithm may be very slow, take a long time, and maybe because of its time frame, the problem becomes practically unsolvable. Or whether there's an algorithm that can find the solution quickly, meaning in polynomial time. That's what the P stands for. So the question is, are all problems in MP, all problems for which there's an algorithm, can they always be solved by, for want of a better phrase, a simple algorithm? And the most famous version of this is perhaps the travelling salesman problem. Given a list of cities and the distance between each pair of cities, what's the shortest possible route that visits each city exactly once and returns to the original city? And to date it has not been proven that this particular problem can be solved in polynomial time. And I think most mathematicians and computer scientists, of course this is of interest to computer scientists as well, believe that it's not true. And this problem is also on another list that I'll talk about in a moment. Financial math could be regarded as an area of mathematical physics, and again it's looking at the well-posedness of the differential equations that represent the models. Navier-Stokes equations are the equations that govern the motion of fluids and gases. And there are well-defined differential equations that represent the models that one is studying. So to look at to analyze questions in terms of the existence of solutions, smoothness of solutions, which is basic analysis studying the behavior of the differential equations, is, I would propose, a true problem in mathematical physics, and is one of the types of problems that I think Hilbert had in mind when he was talking about formulating or axiomizing theoretical physics. Just to give you an idea, because of course when talking about mathematical physics there are various areas that one can consider, and fluid mechanics is probably the most important. So just a comment about the types of questions that arise. Firstly, solutions of these equations. Euler's equations are a set of equations describing some particular systems in applied mathematics. These solutions develop singularities, so how to study these solutions. Finding proofs for the existence of singularities is hard. You can get shock waves occurring. How do you treat shock waves? Many solutions of physical interest are said to be weak. So can we prove theorems on weak solutions? Where I won't say what I mean by weak, but solutions that have certain types of properties in an integral sense. And again, there's been some progress in looking at these types of problems, but no general theory has been presented. Also, around the turn of the century, the millennium, the Clay Institute of Mathematics in 2000 presented seven important problems in mathematics, and also offered a prize of $1 million US. Of the questions, the 7 questions that were posed, one has been solved, namely the aforementioned Poincare conjecture, and the Other 6 include the Riemann hypothesis, M versus MP, and the existence of smoothness of Navier-Stokes equations, and 3 more. M1, pure mathematics, M3, pure mathematics. M2 is a similar problem to the problem in fluid mechanics, in the sense that there's a theory called Yang-Mills theory, and there's a quantum version of this theory which is well posed and written down in terms of differential equations, and so there will be mathematical questions about the system of equations and of the physical implications. So this is basically looking at something like Yang-Mills theory or Maxwell's theory of electromagnetism, and asking questions about the well-posedness of the differential equations. Here's a little comment about what the mass gap problem is itself, but basically it's the field of studying the differential equations in Einstein, in Yang-Mills, or in Maxwell theory. I'll stop there for the time being.